250 million years from now, Earth's continents will collide. Not gradually, not gently, violently. Africa will crush into Eurasia. The Americas will slam into the combined Afro-Eurasian mass. Australia will collide with Asia from the south. Every continent, every landmass, every island will merge into a single supercontinent. Geologists call it Pangaea Ultima, the last Pangaea, and it will be a death trap. The interior of this supercontinent will sit more than 3,000 kilometers from any ocean. No rain will fall there, not for millions of years. Summer temperatures will reach 70 degrees Celsius. Winter temperatures will plunge to -40. The seasonal temperature swing will exceed 100 degrees. Monsoons at the coasts will generate winds exceeding 500 kilometers per hour, making modern hurricanes look like gentle breezes. Mountains higher than the Himalayas will rise along collision zones, blocking moisture, turning the interior into a furnace. 90% of the land surface will be uninhabitable. Animals will retreat to narrow coastal strips, maybe 500 kilometers wide, clinging to the edges of the supercontinent where ocean moisture still reaches. The interior will be sterile, empty, a hell planet hiding inside Earth. And life, complex life, will face its next great filter. Computer models predict 60 to 80% of terrestrial species will go extinct. Not from an asteroid, not from a volcano, from geography, from the simple fact that when continents unite, climate becomes extreme, and extreme climate kills. This isn't speculation, this is physics. Plate tectonics are already moving the continents toward this collision. Africa is closing the Mediterranean Sea at 2.5 centimeters per year. Australia is converging with Antarctica and approaching Asia at 7 centimeters per year. The Atlantic Ocean, currently widening, will eventually reverse. Subduction zones will form along its margins. The ocean will begin to close, and in 250 million years, give or take 50 million, the continents will meet. And here's the thing. This has happened before, at least 6 times. Earth has assembled and shattered supercontinents repeatedly over the last 3 billion years. And every time a supercontinent forms, life suffers. Every time one breaks apart, life recovers. We are living right now in the breakup phase, the dispersed phase, the calm between catastrophes, the safest time climatically in Earth's history. But the convergence has already begun. The next extinction is already scheduled. And the only question is whether we can learn from the last 6 cycles how life survives the assembly and thrives during the breakup. Before we dive in, please consider subscribing and liking this video. Your support truly helps us continue this work. Thank you. 252 million years ago, Earth experienced the worst mass extinction in its history. 96% of marine species went extinct. 70% of terrestrial vertebrate families disappeared. The fossil record shows a world teeming with life, then a boundary layer, then a world nearly empty. Geologists call it the Permian-Triassic extinction, the Great Dying. And for decades, the cause was debated. Volcanism, ocean anoxia, climate change, asteroid impact, all plausible, all contributing, but none fully explaining the scale. Then researchers started looking at the configuration of the continents, and they realized something. At the time of the extinction, all of Earth's landmasses were united into a single supercontinent, Pangaea. The assembly had completed roughly 100 million years earlier, around 335 million years ago. And for that entire span, From assembly to extinction, the climate had been getting worse, more extreme, more hostile, more deadly. Pangaea stretched from pole to pole. Its interior sat more than 3,000 kilometers from the nearest ocean. To understand what that means, consider modern Eurasia. Moscow is roughly 2,000 kilometers from the Atlantic. It experiences continental climate, cold winters, hot summers, seasonal swings of 50 degrees Celsius or more. Now imagine being 3,000 kilometers inland, 1,500 kilometers farther than Moscow, in an era before polar ice caps moderated global temperatures, before the Himalayas and Rockies created rain shadows, before the Atlantic and Pacific currents redistributed heat. The interior of Pangaea experienced temperature swings that modern Earth never sees. Summer temperatures in the deep interior likely exceeded 50 degrees Celsius. Some models push it to 70. Winter temperatures plunged below freezing. Rainfall was effectively zero for thousands of kilometers. The land was desert, perpetual, unrelenting desert, hotter than the Sahara, drier than the Gobi, and larger than both combined. Geologists have a term for this: continentality, the degree to which a location's climate is influenced by its distance from the ocean. Oceans moderate temperature. Water heats and cools slowly. Coastal areas experience mild climates. Interiors experience extremes. And the formula is brutal. The seasonal temperature range increases roughly with the square of the distance from the ocean. Double the distance, quadruple the temperature swing. At 3,000 kilometers inland, the seasonal variation becomes incompatible with most forms of complex life. But the interior wasn't the only problem. The coasts of Pangaea experienced their own horrors. Monsoons, massive continent-scale monsoons, driven by the temperature differential between the ocean and the superheated interior. During summer, the interior heated up, creating a low-pressure zone that sucked moisture from the ocean. Winds accelerated to 300, 400, 500 kilometers per hour. Rain fell in torrential bursts, flash floods carving canyons, then months of drought. The coastal zones were habitable, barely, but they were violent, unpredictable. Ecosystems struggled to adapt. And then there was the ocean, Panthalassa, the world ocean. With all continents united on one side of the planet, the ocean occupied the other 70%. A single, vast body of water, larger than the Pacific, Atlantic, and Indian Oceans combined. And because of its size, its circulation was slow. Currents that normally redistribute heat and oxygen became sluggish. Deep waters stagnated. Oxygen levels dropped. Anoxia spread. In a healthy ocean, surface waters rich in oxygen sink at the poles, travel along the ocean floor, and rise at the equator, completing a circulation loop that takes roughly 1,000 years. This thermohaline circulation keeps the deep ocean oxygenated. But in Panthalassa, the circulation weakened. Surface waters didn't sink efficiently. Deep waters didn't rise. The bottom layers became anoxic. And worse, they became sulfidic. Hydrogen sulfide, a poison, began to accumulate. In extreme cases, it bubbled up to the surface, poisoning shallow marine ecosystems and even releasing toxic gas into the atmosphere. So by the time the Permian-Triassic extinction arrived, Pangaea had spent 100 million years setting the stage. The interior was uninhabitable. The coasts were violent. The ocean was dying. And then the Siberian traps erupted. 3 million cubic kilometers of lava, released over 1 million years. enough to cover the continental United States 3 kilometers deep. The eruptions released carbon dioxide, sulfur dioxide, methane, greenhouse gases. The planet warmed by 10 degrees Celsius, maybe more. Ocean anoxia intensified. Hydrogen sulfide reached the surface, and the already stressed biosphere collapsed. But here's the key point. The Siberian Traps eruptions were bad, catastrophic, but they weren't unique. Earth has experienced other large igneous provinces: the Deccan Traps, the Central Atlantic Magmatic Province, the Columbia River basalts, all comparable in scale, and none caused extinctions as severe as the Permian Triassic. The difference was the supercontinent. Pangaea's configuration amplified the damage. The extreme continentality, the stagnant ocean, the climatic instability. The supercontinent turned a volcanic crisis into a planetary near-death experience. Fossil evidence supports this. In the interior of Pangaea, paleontologists find almost no vertebrate fossils. Not because animals didn't exist, but because they couldn't survive there. The rocks are there, the sediments are there, but the bones aren't. Life avoided the interior. It clung to the coasts. And when the coasts became uninhabitable during the extinction, there was nowhere to go. The animals died, en masse. Bone beds in South Africa, Russia, China show thousands of skeletons concentrated in former river valleys. Mass die-offs, droughts killing entire herds, populations trapped between the deadly interior and the collapsing coasts. This is what supercontinents do. They concentrate land. They create extreme continentality. They destabilize climate. They make oceans stagnant. And when other stresses hit, volcanic eruptions, asteroid impacts, climate shifts, the supercontinent configuration turns a crisis into a catastrophe. Pangaea didn't just host the Permian Triassic extinction, it enabled it. It made it inevitable. And Pangaea wasn't the first supercontinent to kill. It was just the most recent. To understand how continents collide, you need to look at the scars, the sutures, the places where ancient oceans closed and land masses welded together. And one of the most famous sutures on Earth runs through Scotland. 500 million years ago, Scotland and England were separated by an ocean, not a narrow sea, an ocean, 4,000 kilometers wide. Geologists call it the Iapetus Ocean, named after the Greek Titan, father of Atlas. On one side of the Iapetus sat Laurentia, the ancient core of North America, which included what would become Scotland. On the other side sat Baltica, the ancient core of Europe, which included England. And between them, 4,000 kilometers of oceanic crust, spreading at a mid-ocean ridge, subducting at trenches, doing what oceanic crust does: existing, growing, shrinking, dying. But continents don't stay apart forever. Driven by mantle convection, the tectonic plates carrying Laurentia and Baltica began to converge. The Iapetus Ocean began to close. Slowly, 5 centimeters per year, 10 centimeters in a good year. Doesn't sound like much. But over 10 million years, that's 500 to 1,000 kilometers. Over 50 million years, the ocean was gone. The collision, when it came, was not gentle. Laurentia and Baltica slammed together around 420 million years ago, during an event called the Caledonian Orogeny. Orogeny, mountain building, a polite term for what is essentially a planetary-scale car crash. The oceanic crust between the continents, denser than continental crust, subducted, sank into the mantle, melted. The continental margins, too buoyant to subduct, crumpled, folded, thickened. Rocks that had been at sea level were thrust upward, 10 kilometers, 15 kilometers. Mountains formed, not modest hills. Mountains rivaling the modern Himalayas, peaks exceeding 8,000 meters. The energy released was staggering. Every time two continental plates collide, the friction generates heat. Rocks melt, magma rises, volcanoes erupt, and the sheer mechanical energy of billions of tons of crust grinding together produces earthquakes, constantly, for millions of years. Magnitude 7, magnitude 8, magnitude 9, not once, not occasionally, regularly. Imagine living in a world where magnitude 8 earthquakes happen every few decades, every few years, where the ground shakes so often that stability is the anomaly. That was the Caledonian orogeny. Today, if you travel to Scotland, you can still see the scar. The Iapetus suture runs roughly along the Scottish-English border, from the Solway Firth in the west to Berwick-upon-Tweed in the east. On one side of the suture, the rocks are Laurentian, ancient, over 1 billion years old. On the other side, the rocks are Baltican, slightly younger, different chemistry, different fossils, same planet, different origins. The suture is where they met, where the ocean between them was consumed, where two continents became one. But the suture isn't just a line on a map. It's a three-dimensional structure, a deep wound in the Earth's crust. And modern seismic tomography, a technique that uses earthquake waves to image the Earth's interior, has revealed something remarkable. The Iapetus oceanic slab, the crust that subducted 420 million years ago, is still there, still visible, 400 kilometers deep in the mantle, a ghostly remnant of a dead ocean. Denser than the surrounding mantle, it shows up in seismic images as a cold, high-velocity anomaly, a fossil, not a biological fossil, a geological fossil, the corpse of an ocean entombed in the Earth's interior, slowly sinking toward the core. This is what happens when continents collide. Oceans die, mountains rise, and the evidence remains, written in rock for hundreds of millions of years. The Scottish Highlands, those rugged, beautiful mountains, are the eroded roots of the Caledonian Ranges. Ben Nevis, the highest peak in the British Isles, stands 1,345 meters tall, impressive by modern European standards. But 400 million years ago, the mountain at that location was 8,000 meters tall, taller than Everest. What you see today is the base, the foundation. The rest, 6,000 meters of rock, has been eroded away. Carried grain by rivers, glaciers, wind, into the North Sea, the Atlantic, the sedimentary basins surrounding Scotland. And the Iapetus suture is just one of dozens. Pangaea, the supercontinent that existed 250 million years ago, was assembled from multiple collisions. Laurentia and Baltica collided, forming the Caledonides. Laurentia and Gondwana collided, forming the Appalachians and the Variscan Mountains of Europe. Siberia and Baltica collided, forming the Ural Mountains. Each collision closed an ocean. Each collision built mountains. Each collision left a suture. And if you look at a geological map of Pangaea, you see a patchwork, a quilt of ancient continents stitched together by sutures, each representing an ocean that no longer exists. The Appalachians tell a similar story. Today, they are gentle, rolling mountains. The highest peak, Mount Mitchell in North Carolina, stands 2,000 meters. Beautiful, but not dramatic, not Himalayan. But 300 million years ago, during the Alleghenian orogeny, When Gondwana collided with Laurentia, the Appalachians were Himalayan, 8,000 meters, maybe higher. The rocks are still there, metamorphosed, folded, faulted, evidence of the immense pressures and temperatures they experienced during collision. But the peaks are gone, eroded, flattened by 300 million years of weathering. Every mountain range on Earth tells the story of a collision. The Himalayas, currently the tallest, record the ongoing collision between India and Asia, which began 50 million years ago. The Alps record the collision between Africa and Europe. The Urals record the collision between Siberia and Baltica. Mountains are not permanent features. They are temporary, transient, symptoms of continental collision, built over tens of millions of years, eroded over hundreds of millions, and eventually, inevitably, reduced to flat plains. The cycle is relentless. Continents collide, mountains rise. Erosion wins, but the scars remain, the sutures, the deep structures, the subducted slabs. And by studying these scars, geologists can reconstruct the history of supercontinents. They can map ancient collisions, trace ancient oceans, and predict future collisions. Because the process hasn't stopped. It's still happening. Right now, the Mediterranean Sea is closing. Africa is colliding with Europe. The Alps are rising. The Himalayas are rising. The next supercontinent is already under construction. But before we get to the future, we need to go further back. Because Pangaea wasn't Earth's first supercontinent. It wasn't even the second, or the third. Earth has been assembling and shattering supercontinents for at least 3 billion years. And each cycle left its mark, in the rocks, in the fossils, in the very structure of the continents we walk on today. 3 billion years ago, Earth was a very different planet. Hotter, more volcanically active, no oxygen in the atmosphere, no ozone layer, ultraviolet radiation bathing the surface. Life existed, but it was simple, single-celled, bacterial, archaeal, hiding in the oceans, protected from the UV by water. The continents were small, fragments, cratons, pieces of stable, ancient crust that had cooled and solidified from the molten chaos of Earth's early history. But even then, plate tectonics was operating. Continents moved, collided, assembled. The oldest cratons still exist. The Kaapvaal Craton in South Africa dates to 3.6 billion years. The Pilbara Craton in Western Australia dates to 3.5 billion years. These are the most ancient pieces of continental crust on Earth, and geologists have found evidence, tentative but intriguing, that these cratons were once part of a supercontinent. The first supercontinent. They call it Ur. Ur is speculative. The evidence is fragmentary. Matching 3 billion-year-old rocks across continents separated by oceans is difficult. But the hypothesis is this. Around 3 billion years ago, Kaapvaal, Pilbara, and possibly other cratons assembled into a landmass. Not large by modern standards, maybe the size of Greenland, but significant. The first time Earth's continental fragments came together. The first supercontinent. The evidence comes from zircon crystals. Zircons are tough, nearly indestructible. They survive erosion, metamorphism, even subduction. And they contain uranium, which decays to lead at a known rate. By measuring the ratio of uranium to lead, geologists can date the zircon, determine when it crystallized. And zircons from Kaapvaal and Pilbara show matching ages around 3 billion years. Matching chemistry, matching isotopic signatures, suggesting a shared origin. a shared tectonic event, assembly into Ur. Ur didn't last long, maybe 100 million years, maybe less. Archean plate tectonics was faster than modern plate tectonics. The mantle was hotter, convection was more vigorous, plates moved faster. Supercontinents assembled quickly and broke apart quickly. By 2.9 billion years ago, Ur had likely rifted. The cratons separated, drifted apart, and the cycle began again. The next supercontinent is less speculative. Kenorland, 2.7 billion years ago. The name comes from the Kenoran orogeny, a mountain-building event that affected the Superior Craton in Canada around that time. Kenorland included the Superior Craton, the Slave Craton, the Karelia Craton in Russia, and possibly the Yilgarn Craton in Australia. It was larger than Ur, more robust, better documented. The evidence for Kenorland comes from multiple sources. Matching rock types across cratons, matching ages of mountain-building events, matching paleomagnetic directions, the orientation of magnetic minerals in rocks that record the direction of Earth's magnetic field when the rocks formed. If cratons were joined, their paleomagnetic directions should align, and for Kenorland, they do. Roughly, the data is noisy. 2.7 billion years is a long time, but the pattern is there. And here's where it gets interesting. The breakup of Kenorland around 2.5 to 2.1 billion years ago coincides with one of the most important events in Earth's history, the Great Oxidation Event. 2.4 billion years ago, the concentration of oxygen in Earth's atmosphere suddenly increased from trace amounts less than 1% to significant amounts, maybe 5 to 10%. Not breathable by modern standards, but a radical change, and that change transformed the planet. Before the Great Oxidation Event, Earth's atmosphere was reducing. Methane, carbon dioxide, hydrogen, no free oxygen. Oxygen is highly reactive. It doesn't stay free for long. It binds to iron, forming rust. It binds to sulfur, forming sulfates. Any oxygen produced by early photosynthetic bacteria, cyanobacteria, was immediately consumed by reactions with the crust and the ocean. The planet was an oxygen sink. But around 2.4 billion years ago, something changed. The sinks became saturated. All the iron in the ocean had rusted. All the reduced sulfur had oxidized, and oxygen began to accumulate in the atmosphere. And that accumulation, many researchers believe, was linked to the breakup of Kenorland. Here's the hypothesis. When Kenorland was assembled, the interior was dry, desert, continental. Volcanism was concentrated along the margins, and volcanic gases, particularly carbon dioxide, were locked in the interior rocks, not reaching the ocean efficiently. Cyanobacteria, living in the oceans, were producing oxygen, but the weathering of continental rocks was also consuming oxygen. The balance was roughly neutral. But when Kenorland broke apart, rifting occurred. New mid-ocean ridges formed. Volcanism increased. Carbon dioxide was released into the atmosphere. But more importantly, the breakup created new shallow seas, flooded continental margins, epicontinental seas. Perfect habitats for cyanobacteria. Photosynthesis accelerated, oxygen production increased, and this time, because the sinks were saturated, the oxygen accumulated. The Great Oxidation Event was catastrophic for anaerobic life. Oxygen is toxic to organisms that evolved without it. 99% of anaerobic species likely went extinct. It was Earth's first mass extinction, invisible to us because these organisms didn't leave fossils, but devastating nonetheless. The survivors, the organisms that adapted to oxygen or that learned to harness it, inherited a transformed world. A world where aerobic respiration, 20 times more efficient than anaerobic metabolism, became possible. A world where eukaryotes, cells with nuclei and mitochondria, could evolve. A world where complex life became possible. And it all might have been triggered by the breakup of a supercontinent. Kenorland's assembly created a stable, sterile world. Its breakup created chaos, flooded seas, volcanism, and ultimately, oxygenation. Supercontinents, it turns out, don't just kill through climate extremes. They kill through stability, through stagnation, and when they break apart, they unleash creative destruction. The next supercontinent in Earth's history is simultaneously the best documented and the most mysterious. Columbia, also called Nuna, 1.8 billion years ago. It was massive, possibly the largest supercontinent Earth had ever assembled up to that point, stretching 13,000 kilometers from north to south, straddling the equator, dominating the planet. The core of Columbia was Laurentia, the ancient heart of North America. Attached to Laurentia's northern margin was Baltica, the core of Europe. To the east, Siberia. To the south, possibly Australia, or possibly India. The reconstructions vary. 1.8 billion years is far enough back that continental drift has scrambled the evidence, moved the pieces multiple times, closed and opened multiple oceans. What's clear is that most of Earth's continental crust was united. And what's also clear is that the planet, during Columbia's tenure, became extraordinarily boring. Geologists call the period from 1.8 billion to 800 million years ago the Boring Billion. And the name is not sarcastic. It's descriptive. For a billion years, almost nothing happened. Evolutionarily, geologically, climatically, the planet was stuck, stagnant. Eukaryotic cells existed, complex cells with nuclei, mitochondria, internal structures. The machinery for complexity was in place, but nothing was happening with it. No multicellularity, no diversification, no innovation. Life treaded water for a billion years. The fossil record from the Boring Billion is monotonous. Stromatolites, layered structures built by bacterial mats, look the same at 1.8 billion years as they do at 1 billion years. 800 million years. No change. Algae existed, single-celled photosynthesizers. But they didn't evolve. They didn't diversify. They just reproduced, generation after generation, eon after eon, going nowhere. Why? What could freeze evolution for so long? The answer, increasingly, seems to be the supercontinent. Columbia's existence created a planetary environment hostile to evolutionary innovation. And the mechanism was nutrients, specifically phosphorus. Phosphorus is essential for life. DNA contains phosphorus. RNA contains phosphorus. ATP, the energy currency of cells, contains phosphorus. Without phosphorus, biochemistry doesn't work. And phosphorus, unlike carbon or nitrogen, doesn't cycle through the atmosphere. It comes from rocks, from the weathering of continental crust. Rainfall breaks down minerals, releases phosphorus, washes it into rivers, which carry it to the ocean, where it fertilizes phytoplankton, which form the base of the marine food web. But during the Boring Billion, phosphorus delivery to the oceans was unusually low. Why? Because Columbia's interior was dry, desert, minimal rainfall, minimal weathering. The mountains that had been built during Columbia's assembly 1.8 billion years ago had eroded. The continent was flat, and flat, dry continents don't weather efficiently. Phosphorus stayed locked in the rocks. The oceans became nutrient-starved. Phytoplankton productivity dropped. And with it, the entire marine food web stagnated. There's another factor. Tectonic activity during the Boring Billion was unusually low. The rate of zircon production, a proxy for mountain building and continental growth, drops by 50% during this period. Fewer mountains, less volcanism, less tectonic recycling. The planet's internal engine didn't stop, but it idled. And without tectonic activity to drive weathering, to create new topography, to expose fresh rock, the nutrient cycle slowed to a crawl. Columbia, by existing, by being stable, by being flat and dry and geologically quiet, starved the oceans. And starved oceans don't support evolutionary innovation. Life survived, it persisted, but it didn't diversify. It couldn't. There wasn't enough energy, enough nutrients, enough ecological opportunity. Evolution requires variation, selection, and time. The Boring Billion had time, 1 billion years of it, but it lacked the other two. Variation was limited, selection was weak, and the result was stasis. And then, around 1 billion years ago, Columbia began to break apart. Rifting started. New mid-ocean ridges formed. Volcanism increased. Mountains began to rise again. Weathering accelerated. Phosphorus washed into the oceans. Productivity spiked. And within a few 100 million years, eukaryotes began to diversify. The first experiments in multicellularity appeared. Algae formed colonies. Cells started cooperating, specializing. And by 600 million years ago, the Boring Billion was over. Life exploded. The Ediacaran period, the Cambrian explosion, animals. The breakup of Columbia didn't just end the Boring Billion, it enabled everything that came after. Every animal, every plant, every fungus. All of complex life owes its existence to the fact that Columbia broke apart. If it hadn't, if it had remained stable for another billion years, evolution might still be stuck at the single-celled stage. Earth would be a planet of bacteria and algae. Nothing more. Supercontinents, it turns out, are evolutionary traps. Assembly creates stability. Stability creates stagnation. Stagnation creates sterility. And only breakup, only the chaos of rifting and flooding and nutrient release allows life to move forward. The lesson is clear. Stability is not always good. Sometimes the system needs to be disrupted, shaken, broken, for innovation to occur. But Columbia's breakup led to something even more dramatic than the end of the Boring Billion. It led to Rodinia, and Rodinia led to the most extreme climate event in Earth's history, Snowball Earth. 1 billion years ago, as Columbia fragmented, the pieces began to reassemble. Continental drift doesn't stop, it redirects. Fragments that had been moving apart began converging again. And by 1 billion years ago, they had formed a new supercontinent, Rodinia. The name comes from the Russian word for homeland, Rodina, because large parts of Rodinia included the Siberian Craton. Rodinia was configured differently than Columbia. Instead of straddling the equator, Rodinia was centered in the southern hemisphere. Laurentia, the core, sat near the South Pole. East Antarctica was attached to Laurentia's western margin. Australia was attached to the eastern margin. India, possibly, attached to the north. The reconstruction is debated, but the general picture is clear. Rodinia was a polar supercontinent, and its assembly triggered massive mountain building, the Grenville orogeny, 1 billion years ago. Eastern North America collided with something, probably a combination of Amazonia and East Antarctica, producing a mountain range that rivaled the Himalayas. Evidence of the Grenville orogeny is visible today in the Appalachian Mountains, where Grenville age rocks, 1 billion years old, metamorphosed and deformed, form the core of the range. The modern Appalachians are much younger, 300 million years old, but they were built on top of the Grenville roots. The Grenville Mountains were enormous. Estimates based on the volume of eroded material suggest peaks exceeding 10,000 meters, possibly higher. The exact height is uncertain because the peaks are long gone, eroded away over hundreds of millions of years. But what's certain is that they were massive, and their existence had profound consequences for Earth's climate. Mountains drive weathering. Rainfall hits rock. Water infiltrates cracks, freezes, expands, breaks the rock apart. Chemical reactions dissolve minerals. Carbon dioxide from the atmosphere reacts with calcium silicate in the rock, forming calcium carbonate, which is washed into the ocean. This process, called silicate weathering, removes carbon dioxide from the atmosphere, and carbon dioxide is a greenhouse gas. Remove enough of it, and the planet cools. The Grenville Mountains, tall and extensive, weathered intensely. Rainfall was heavy. Rivers were powerful. Carbon dioxide was drawn down. Atmospheric concentrations dropped. And around 720 million years ago, Earth's climate crossed a threshold. The planet froze. Not just the poles, not just the high latitudes. Everywhere. Ice extended from the poles to the equator. Glaciers covered continents. Sea ice covered oceans. Earth became a snowball. Geologists call it the Sturtian glaciation, and it lasted for millions of years, possibly 50 million, possibly longer. The exact duration is uncertain. But what's certain is that it was catastrophic. Under the ice, life clung to survival. Photosynthesis was impossible. No sunlight reached the surface. The ice was kilometers thick. Most marine ecosystems collapsed. Only organisms near deep-sea hydrothermal vents, where heat and chemicals from Earth's interior supported chemosynthetic bacteria, survived. Life didn't go extinct, but it was pushed to the brink, reduced to refugia, tiny pockets of habitability in a frozen world. What ended the snowball? Volcanism. Plate tectonics didn't stop. Volcanoes continued to erupt, and volcanic eruptions release carbon dioxide. Under normal circumstances, that carbon dioxide is removed by weathering. But under snowball conditions, with the continents covered in ice, weathering stopped. Carbon dioxide accumulated, slowly, over millions of years. Volcanic eruption after volcanic eruption, adding carbon dioxide to the atmosphere with no removal mechanism. Eventually, concentrations reached levels high enough to force a thaw. Estimates suggest carbon dioxide levels rose to 350 times pre-industrial levels. A greenhouse effect so intense it melted the ice. And when the ice melted, it melted fast. Within a few thousand years, Earth transitioned from snowball to hothouse. Ice albedo feedback in reverse. White ice reflects sunlight, keeping the planet cold. But once the ice starts melting, darker ocean and land are exposed, which absorbs sunlight, warming the planet further, melting more ice. Runaway warming. The thaw was as extreme as the freeze, and in the aftermath, life began to recover. The Sturtian glaciation ended around 660 million years ago. 50 million years later, Earth froze again. The Marinoan glaciation, another snowball event. lasting another 10 to 15 million years. And then, 635 million years ago, the ice melted for good. And something remarkable happened. Within 40 million years of the final thaw, complex multicellular organisms appeared. The Ediacaran biota, soft-bodied, enigmatic creatures, fronds, discs, quilted forms, nothing like modern animals, but unquestionably multicellular, unquestionably complex. And then, 541 million years ago, the Cambrian explosion, every major animal body plan appearing within 20 million years, eyes evolving, predation beginning, skeletons forming, an evolutionary arms race. The connection between Rodinia's breakup, Snowball Earth, and the Cambrian explosion is still debated. But the timing is suggestive. Rodinia began to rift around 750 million years ago. The rifting coincided with the onset of the Sturtian glaciation. The hypothesis is that rifting, by splitting the supercontinent, disrupted ocean circulation, altered atmospheric circulation, and somehow triggered the freeze. Then, the snowball events, by extinguishing most life and creating extreme selection pressure, cleared the way for evolutionary innovation. The survivors, tough, adaptable, were poised to diversify rapidly once conditions improved. And the breakup of Rodinia created ideal conditions for that diversification. Shallow seas flooded the rifted continental margins. Nutrient-rich waters from upwelling currents fertilized coastal ecosystems. Ecological niches multiplied, and life, freed from the constraints of the snowball, exploded into those niches. Rodinia's existence almost ended complex life before it began. Its breakup enabled complex life to thrive. The supercontinent was a bottleneck, a filter, and the organisms that passed through, that survived the snowball, inherited a world of opportunity. But Rodinia wasn't the last supercontinent to shape life's trajectory. The fragments of Rodinia drifted for 100 million years, then began to reassemble. By 600 million years ago, another supercontinent was forming, Gondwana. Gondwana was not a complete supercontinent, not in the sense of Pangaea or Columbia. Gondwana included Africa, South America, Antarctica, Australia, India, and Arabia, a massive landmass, roughly 100 million square kilometers. But it did not include Laurentia, which remained separate as the continent Laurussia. Nor did it include Baltica or Siberia, which also remained independent. Gondwana was dominant, but not total. And that partial assembly, that incomplete supercontinent, turned out to be crucial for life. Because Gondwana's configuration avoided the worst effects of continentality. It stretched from pole to pole? Yes. But it was narrow. Its interior was never more than 1,500 kilometers from an ocean. Compare that to Pangaea, where the interior was 3,000 kilometers inland. Gondwana's interior was dry, but not sterile. Habitable, if harsh. More importantly, Gondwana's coasts were extensive. Long, complex coastlines with shallow seas. The Cambrian explosion occurred along Gondwana's margins. The Ordovician radiation, the Silurian greening of the land, the Devonian diversification of fish, all happened while Gondwana was the dominant landmass. For 250 million years, from 600 to 335 million years ago, Gondwana hosted some of the most important evolutionary innovations in Earth's history. The colonization of land, the evolution of vascular plants, the evolution of tetrapods, the evolution of amniotes, the group that includes reptiles, birds, and mammals, Why was Gondwana so hospitable? Orientation. It ran north-south, from pole to pole, rather than east-west like Pangaea. That orientation created climate diversity. The northern regions were tropical, the southern regions were temperate or polar, and organisms could migrate along climate gradients, tracking suitable temperatures as continents drifted. Evolution proceeded rapidly because ecological opportunity was abundant. But Gondwana's luck ran out. Around 335 million years ago, Laurussia collided with Gondwana. The Alleghenian orogeny, the Appalachians and the Variscan Mountains of Europe rose, and the continents welded together. Gondwana ceased to exist as a separate entity. It became part of something larger, something more hostile. Pangaea. Pangaea. 335 million years ago. Assembly complete. All of Earth's continental crust united into a single landmass, pole to pole, east to west, covering 20% of Earth's surface. And for the next 80 million years, from 335 to 250 million years ago, life on Pangaea struggled. The interior of Pangaea was hell. Summer temperatures exceeded 60 degrees Celsius. Winter temperatures dropped below -40. No rain fell. The fossil record from Pangaea's interior is sparse. Almost no vertebrates, a few hardy reptiles, insects, plants adapted to extreme drought, but nothing diverse, nothing abundant. Life avoided the interior. The coasts were better. Monsoons brought rain, violently and unpredictably. Forests grew along the edges. The Carboniferous coal forests, 300 million years ago, thrived in the humid coastal zones. Giant insects, dragonflies with 70-centimeter wingspans, roamed the swamps. Amphibians diversified, but even the coasts were constrained. The single ocean, Panthalassa, circulated sluggishly. Anoxia spread in the deep basins. Marine diversity stagnated. And then the Siberian traps erupted. 252 million years ago. 3 million cubic kilometers of lava. Over 1 million years. The eruptions released carbon dioxide, methane from organic-rich sediments, sulfur dioxide, chlorine. The planet warmed by 10 degrees. Ocean temperatures in the tropics reached 40 degrees Celsius. Marine organisms unable to regulate temperature cooked. On land, the already extreme heat became lethal. 50 degrees interior, 60 degrees during heat waves. Animals couldn't thermoregulate. They died. The extinction was global. 96% of marine species, 70% of terrestrial vertebrate families. The fossil record shows bone beds, mass graves, thousands of skeletons, temnospondyl amphibians, therapsid reptiles, piled together in river valleys where they sought water during droughts and died when the water ran out. The Permian Triassic extinction was the closest life has come to total annihilation. And while the Siberian traps pulled the trigger, Pangaea loaded the gun. Recovery took 10 million years, longer than any other extinction. The early Triassic was a ghost world, low diversity, simple ecosystems, a few opportunistic species dominating. Coal gaps in the fossil record, periods where no coal formed because there weren't enough plants to create peat. It wasn't until the Middle Triassic, 240 million years ago, that ecosystems began to resemble their pre-extinction complexity. And what finally saved life? Pangaea's breakup. 180 million years ago, rifting began. The Central Atlantic magmatic province erupted. Massive flood basalts. Normally, flood basalts trigger extinctions, and the camp eruptions did. the Triassic-Jurassic extinction 200 million years ago. But the rifting also did something beneficial. It started breaking Pangaea apart. The Atlantic Ocean began to open, Gondwana separated from Laurasia, interior regions became coasts, climate moderated, rain returned, and life, freed from Pangaea's stranglehold, diversified. The Jurassic, the age of dinosaurs. Not a coincidence. Dinosaurs had existed during the Triassic, but they were minor players, overshadowed by other reptile groups. Once Pangaea broke apart, once climate became more hospitable, dinosaurs radiated. Sauropods evolved. Theropods diversified. The Morrison Formation 150 million years ago shows an ecosystem teeming with giant dinosaurs, herbivores, carnivores. A functional, complex world, all made possible by Pangaea's breakup, and Pangaea continued to fragment. Gondwana itself split. South America separated from Africa. India separated from Antarctica. Australia separated from Antarctica. Each rifting event created new coastlines, new shallow seas, new evolutionary opportunities. By 100 million years ago, the Cretaceous, the continents were dispersed. Climate was moderate. Biodiversity peaked. And then, 66 million years ago, the Chicxulub asteroid hit. The dinosaurs died. But the continents remained dispersed, and mammals, small and opportunistic, radiated into the empty niches. Today, we live in the aftermath of Pangaea's breakup. The continents are scattered, the Atlantic is still widening, the Pacific is still shrinking, but the process hasn't stopped. And it won't. Because plate tectonics is relentless, and the next supercontinent is already under construction. Right now, as you listen to this, the continents are moving. Africa is sliding northward at 2.5 centimeters per year. It doesn't sound fast, but over a million years, that's 25 kilometers. Over 10 million years, 250 kilometers. The Mediterranean Sea, which currently separates Africa from Europe, is doomed. It's closing. The Strait of Gibraltar, the narrow passage connecting the Mediterranean to the Atlantic, will eventually seal shut. And when it does, the Mediterranean will evaporate, become a salt flat, a desert basin 4 kilometers below sea level. This has happened before, 5.3 million years ago, during the Messinian salinity crisis. The Strait of Gibraltar closed temporarily. The Mediterranean dried up within 1,000 years. When it refilled, the resulting waterfall was 1,000 times larger than Niagara Falls. The Zangklane flood. 600 cubic kilometers of water per day pouring through the strait. The Mediterranean refilled in 2 years. But next time, it won't refill. Because next time, Africa won't stop moving. It will collide with Europe. The Alps, currently the product of Africa's ongoing northward push, will grow taller. The Pyrenees will thicken, and eventually the collision will weld the continents together. Africa and Eurasia will become one landmass, Afro-Eurasia. Australia is also moving. Northward, 7 centimeters per year, twice as fast as Africa. Australia is currently colliding with the Pacific Plate along its northern margin. The collision is producing mountains in New Guinea, earthquakes in Indonesia, and in 50 million years, Australia will collide with Southeast Asia. The collision will close the ocean basins between them, build mountains, create another suture, another scar. Australia and Asia will merge. The Atlantic Ocean is also changing. Currently, it's widening. The Mid-Atlantic Ridge, the divergent boundary running down the center of the Atlantic, is producing new oceanic crust, pushing the Americas away from Europe and Africa at about 2.5 centimeters per year. This has been happening for 180 million years, since Pangaea began to break apart. But the Atlantic won't widen forever. Eventually, subduction zones will form along its margins. The oceanic crust, old and dense, will begin to sink back into the mantle, and the Atlantic will begin to close. When? The models vary. Some predict subduction initiation within 50 million years. Others suggest 150 million years. But eventually, it will happen. And when it does, the Americas will begin to converge with Afro-Eurasia. The Atlantic will shrink, disappear, and the continents will collide. Again. Geologists have proposed three main scenarios for the next supercontinent. The first is called Pangaea Ultima, sometimes spelled Pangaea Proxima. In this scenario, the Atlantic closes completely. The Americas collide with Afro-Eurasia. The supercontinent forms roughly where Pangaea was, centered on the equator, with the former Atlantic basin as its heart. Pangaea Ultima would be massive, all continents except Antarctica united, and its climate would be brutal. The second scenario is called Orica. In this scenario, the Pacific Ocean closes instead of the Atlantic. Asia, Australia, and the Americas converge on the Pacific Basin. The Atlantic continues to widen. Afro-Eurasia drifts away from the Americas, and the supercontinent forms around the current Pacific. Orica would also be massive, possibly larger than Pangaea Ultima. But its climate might be slightly less extreme because the configuration would be different, less concentrated, more coastline relative to interior. The third scenario is Amasia. In this scenario, the continents slide northward, converging around the Arctic. The North Pole becomes the center of the supercontinent. The Arctic Ocean closes, and Amasia forms as a polar supercontinent, like Rodinia. This scenario is less likely because it requires most continents to move in the same direction simultaneously. But it's possible, and if it happens, Amasia's climate would be extreme in a different way. Polar, ice-covered, hostile not from heat, but from cold. Which scenario is most likely? Current models favor Pangaea Ultima. The reason is simple. The Atlantic Ocean is old. Its crust, especially near the margins, is dense, cold, ready to subduct. The Pacific, by contrast, is young near the East Pacific Rise, less dense, less likely to subduct there. But the Western Pacific, where the crust is older, already has subduction zones. The Pacific is shrinking. The Atlantic is widening. Extrapolate these trends forward, and Pangaea Ultima is the result. 250 million years from now, give or take 50 million. Pangaea Ultima assembles. The Americas collide with Afro-Eurasia. Australia, already merged with Asia, joins the supercontinent from the east. Antarctica, isolated at the South Pole, might remain separate, or it might drift northward and join as well. The result is a single landmass stretching from pole to pole, east to west, covering 30% of Earth's surface, and the interior of Pangaea Ultima will be uninhabitable. Climate models are unambiguous. The center of the supercontinent will sit 3,500 kilometers from the nearest ocean. Summer temperatures will reach 70 degrees Celsius, possibly higher. Winter temperatures will drop to -30. The seasonal swing will exceed 100 degrees. No rain will fall in the interior for millions of years. It will be a hyper-arid mega-desert. The Sahara, the Gobi, the Australian outback, all combined, multiplied by 10 and turned up to lethal intensity. Why so extreme? Continentality. Distance from the ocean matters. Oceans store heat. During summer, they absorb solar energy, moderating coastal temperatures. During winter, they release stored heat, keeping coasts warmer. But that effect diminishes with distance. 1,500 kilometers inland, the ocean's influence is weak. 3,000 kilometers inland, it's negligible. The interior is thermally decoupled from the ocean. It heats and cools based purely on solar input and radiative loss. No buffering, no moderation, and 3,500 kilometers is beyond any modern analog. The most continental location on Earth today is probably in Central Asia, around 2,000 kilometers from the nearest ocean. And even there, summer temperatures reach 50 degrees, not 70. Pangaea, Ultima's interior will be 20 degrees hotter. That's the difference between uncomfortable and lethal. Mammals cannot survive 70-degree ambient temperatures, not for long. Mammalian thermoregulation depends on evaporative cooling, sweating, panting. But when the ambient temperature exceeds body temperature, evaporative cooling becomes insufficient. The body gains heat from the environment. Core temperature rises. Hypothermia sets in. Organs fail. Death follows within hours. Some reptiles can tolerate higher temperatures. Lizards, snakes, desert specialists. They behaviorally thermoregulate. Hide in burrows during the day, emerge at night. But even they have limits. 70 degrees is near the upper bound for most reptiles. And in Pangaea, Ultima's interior, nighttime temperatures will still be hot. 40 degrees, 50 degrees, no relief. The only organisms that might thrive in Pangaea Ultima's interior are extremophiles, heat-tolerant bacteria, archaea, perhaps some hardy insects. But complex animals, vertebrates, will be absent. The interior will be sterile. Life will retreat to the coasts, the margins of the supercontinent, where ocean influence still reaches, where rain occasionally falls. Climate models predict habitable zones extending perhaps 500 kilometers inland from the coast. Beyond that, desert. Beyond 1,000 kilometers, death. 90% of the land surface uninhabitable. Biodiversity concentrated in narrow coastal strips. And the coasts themselves will be violent. The temperature differential between the superheated interior and the cooler ocean will drive monstrous monsoons. During summer, the interior heats up, creating a massive low-pressure zone. Air from the ocean rushes inland to fill the void. Wind speeds accelerate, 300 kilometers per hour, 400, 500. Hurricanes are rated Category 5 at 250 kilometers per hour. Pangaea. Ultima's monsoons will exceed that regularly. Trees, if they exist, will be stunted, bent, shaped by constant wind. Flash floods will carve the landscape during monsoon season. And then, for the rest of the year, drought. The ocean, Panthalassa Ultima, will also suffer. With all continents united on one side of the planet, the ocean will occupy the other 70%, larger than the Pacific, deeper, more sluggish. Circulation will weaken, deep waters will stagnate, oxygen depletion will spread, anoxic zones will expand. Marine life will concentrate near the surface, near the coasts where oxygen is available. The deep ocean will become a dead zone. And then there's the extinction. Paleontologists have modeled the biodiversity impact of Pangaea Ultima. The results are grim. 60 to 80% of terrestrial species predicted to go extinct. Not from a single catastrophic event, from gradual attrition, habitat loss, climate stress, range contraction. As the supercontinent assembles, interior regions dry out. populations become isolated. Gene flow ceases. Isolated populations go extinct one by one. And by the time assembly is complete, the damage is done. Marine extinction rates will be lower, 40%, maybe 50%. The ocean, even a stagnant one, is more homogeneous than land. Marine organisms can migrate more easily. But the combination of anoxia, warming, and reduced productivity will still take a toll. Coral reefs, already sensitive to temperature, will likely disappear. Calcifying organisms struggling with ocean acidification will decline. The food web will simplify. This is not speculation, this is projection, based on physics, based on plate tectonics, based on climate models. Pangaea Ultima is coming. The continents are already moving toward it. The collision is inevitable. But here's the crucial point. Life will survive. It always does. 60 to 80% extinction sounds catastrophic, and it is. But 20 to 40% survival means continuity. Life persists. And once Pangaea Ultima breaks apart, once the supercontinent rifts and fragments and the continents disperse again, life will recover. Diversity will rebound. New species will evolve to fill empty niches. The pattern repeats. Because supercontinents don't last forever. Pangaea Ultima, like Pangaea, like Rodinia, like Columbia, will eventually rift. The interior, hot and dry, will become tectonically unstable. Mantle plumes will rise beneath the supercontinent, heating the crust from below. The crust will thin, stretch, crack. Rift valleys will form. Volcanoes will erupt, and the supercontinent will begin to split. The timescale for breakup is uncertain. Pangaea lasted about 150 million years before rifting began. Columbia lasted perhaps 200 million years. Rodinia lasted 250 million years. The duration seems to increase with each cycle, possibly because the mantle is cooling, convection is slowing, and plate tectonics is weakening. But even if Pangaea Ultima lasts 300 million years, it will eventually break apart. And when it does, the survivors will radiate. Life will flood back into the interior. Coastlines will expand. Shallow seas will form. Nutrients will flow. Productivity will spike. And evolution, suppressed during the supercontinent's tenure, will accelerate. New body plans, new adaptations, new ecosystems. The breakup will be an evolutionary renaissance. This has happened 6 times already. Ur assembled and broke apart. Knorland assembled and broke apart. Columbia assembled and broke apart. Rodinia assembled and broke apart. Gondwana assembled and broke apart. Pangaea assembled and broke apart. And each time the breakup enabled life to diversify, to innovate, to expand. The supercontinent cycle is not just a geological curiosity, it's a biological necessity, a forcing function for evolution. Without supercontinents, Earth's biodiversity would be lower, more static, less dynamic. The assembly breakup cycle creates ecological instability. And instability, as uncomfortable as it is, drives adaptation. Organisms that can tolerate change, that can migrate, that can specialize or generalize as needed, survive. Those that can't go extinct. And over time, the survivors become more resilient, more diverse, more complex. The supercontinent cycle is Earth's way of pruning the tree of life, cutting back the branches, forcing new growth. It's brutal, wasteful. Millions of species die, but the result is a biosphere that's constantly evolving, constantly adapting, never static, never stagnant. And we, Homo sapiens, are products of this cycle. Our lineage, primates, evolved during the breakup of Pangaea. Mammals radiated after the Cretaceous Paleogene extinction, which occurred while the continents were dispersed. Our genus, Homo, emerged 2 million years ago, during the most dispersed phase of the current cycle. We are creatures of the breakup. Our existence depends on the fact that the continents are scattered, climate is moderate, and ecological opportunity is abundant. If we had evolved during a supercontinent assembly phase, during Pangaea's formation or Rodinia's tenure, we probably wouldn't be here. The climate would have been too extreme, the habitable zones too narrow, the extinction pressure too high. Our lineage might have survived in some coastal refugium, clinging to existence. But it wouldn't have thrived, wouldn't have diversified, wouldn't have developed the ecological breadth and adaptability that characterizes modern humans. We are lucky, temporarily lucky. We exist during the safest phase of the supercontinent cycle, the dispersed phase, the calm between catastrophes. And that luck has allowed us to build civilization, to develop agriculture, to invent technology, to spread across the planet. None of that would have been possible during a supercontinent assembly phase. But our luck is temporary. In 100 million years, the continents will begin to converge. In 250 million years, Pangaea Ultima will form. And if humanity or our descendants still exist, they will face the same challenges that every other lineage has faced during supercontinent assembly. Retreat to the coasts, adapt to extreme climate, survive the extinction, wait for the breakup. Can we? It's an interesting question. Humans are adaptable. We occupy every continent except Antarctica, and we've even built research stations there. We thrive in deserts, tundra, rainforests, mountains. We can engineer our environment, build shelters, generate power, synthesize food. In principle, we could survive Pangaea Ultima's interior using technology, underground habitats, climate control, artificial ecosystems. But the scale is daunting. Pangaea Ultima's interior will be larger than all of Earth's current deserts combined. Sustaining a technological civilization in such an environment for millions of years would require resources, infrastructure, and coordination beyond anything humanity has achieved. And that assumes we don't face other existential risks in the meantime. Climate change, nuclear war, asteroid impact, artificial intelligence, pandemics, any of which could end civilization long before Pangaea Ultima becomes relevant. More likely, if humanity survives to see Pangaea Ultima, we will have changed, evolved, speciated, become something no longer recognizably Homo sapiens. Our descendants might be adapted to high temperatures, might have different metabolisms, might be cyborgs, might be digital, might have left Earth entirely, spreading to other planets, other star systems, rendering the supercontinent cycle irrelevant. Or we might be gone, extinct, replaced by whatever lineage adapts best to Pangaea Ultima's conditions. Reptiles, insects, something we can't predict. Evolution doesn't have a goal. It doesn't favor complexity or intelligence. It favors whatever survives. And in Pangaea Ultima's furnace, survival might not require a large brain. It might require a small body, low metabolic rate, heat tolerance, behavioral flexibility, traits that humans in our current form lack. The supercontinent cycle is humbling. It reminds us that we are not permanent, not inevitable, not exempt from the forces that shape all life. We are participants in a process that has been running for 3 billion years and will continue for billions more. Our moment is brief, a few 100,000 years out of billions. And when Pangaea Ultima forms, whether we're there to see it or not, life will continue. The cycle will continue. But let's return to the present, to the here and now. Because while Pangaea Ultima is 250 million years away, the convergence is already visible, already measurable, already shaping the planet. The Mediterranean is closing, 2.5 centimeters per year. In geological terms, that's fast. In human terms, it's imperceptible. But it's happening. The African plate is colliding with the Eurasian plate. The boundary between them is not a clean line. It's a messy, diffuse zone of faults, folds, and mountain ranges. The Atlas Mountains in Morocco, the Alps in Europe, the Apennines in Italy, the Dinarides in the Balkans, all products of Africa's northward push. And the collision is not gentle. Italy experiences frequent earthquakes. Turkey sits on the North Anatolian Fault, where the Arabian Plate, also being pushed by Africa, slides past the Eurasian Plate. The 1999 Izmit earthquake killed 17,000 people. The 2023 Turkey-Syria earthquake killed over 50,000. These are not random disasters. They are symptoms of continental collision. Africa pushing north, Eurasia resisting. The crust crumpling, faulting, quaking. Greece experiences similar activity. The Aegean region is being stretched as the African plate subducts beneath it. Crete, Rhodes, the Cyclades Islands are all rising. The seafloor is subsiding. Subduction zones are active. And every few decades, a major earthquake strikes. The cost in human lives is measured in thousands. The cost in infrastructure, billions. And it will continue for millions of years until the collision is complete. The Himalayas are also growing. India, moving northward at 5 centimeters per year, is still colliding with Asia. The collision began 50 million years ago. The Himalayas started rising, and they haven't stopped. Everest grows 4 millimeters per year, not from volcanic activity, from uplift. The crust is being compressed, thickened, pushed upward, and erosion is carving it down simultaneously. The balance between uplift and erosion determines the height. Currently, uplift is winning. The Himalayas are the tallest mountains on Earth, and they're still growing. But the collision is doing more than building mountains. It's changing climate. The Himalayas block moisture from the Indian Ocean, creating the rain shadow that makes the Tibetan Plateau dry. They force the jet stream to split, influencing weather patterns across Asia. They drive the Asian monsoon, which feeds 2 billion people. The collision between India and Asia has shaped human history, enabled agriculture, built civilizations, and it's still happening. Australia's convergence with Asia is also active. The collision is less advanced than India-Asia. Australia is still separated from Southeast Asia by ocean basins. But the gap is closing. New Guinea, on Australia's northern margin, is colliding with the Pacific Plate. Mountains are rising. Earthquakes are common. And in 50 million years, Australia will merge with Asia. Another suture, another scar. The Atlantic, meanwhile, is still widening. For now, the Mid-Atlantic Ridge is active. Lava erupts. New crust forms. The Americas drift west. Europe and Africa drift east. The Atlantic grows wider by a few centimeters per year. But this is temporary. The Atlantic is old. Its crust, especially near the margins, is dense. Eventually, it will become dense enough to subduct. And when it does, the process will reverse. The Atlantic will shrink, and the Americas will begin moving toward Afro-Eurasia. Subduction initiation is unpredictable. It depends on the strength of the crust, the temperature of the mantle, the configuration of stresses. Models vary. Some predict subduction within 50 million years. Others suggest 150 million years. But it will happen. The Atlantic will close, and Pangaea Ultima will form. And when it does, the extinction will follow. Not immediately. Supercontinent assembly takes time. 100 million years, 200 million years. Continents collide slowly. Mountains rise gradually. Climate changes incrementally. But the trend is inexorable. Interior regions dry out. Temperature extremes intensify. Habitable zones shrink. Species go extinct. Not in a single event. In a slow, grinding attrition. A death by 1,000 cuts. And there's nothing life can do to stop it. Plate tectonics is driven by mantle convection. Heat from Earth's interior. Radioactive decay of uranium, thorium, potassium in the mantle, generating heat, driving convection, moving plates. This process is beyond life's control. Life can change the atmosphere. Oxygen, carbon dioxide, methane. Life can change the surface. Weathering, soil formation, erosion. But life cannot change plate tectonics, cannot stop continents from moving, cannot prevent supercontinent assembly. All life can do is adapt, migrate, survive, wait for the breakup, and then radiate, diversify, reclaim the interior, thrive, until the next assembly. And the cycle repeats. This is Earth's rhythm. Assembly, tenure, breakup, repeat. 6 times so far, possibly more in the deep past, before the rock record becomes too fragmentary to read. And it will continue, for as long as Earth's interior remains hot, for as long as plate tectonics operates, billions of years, until the planet cools, until the mantle solidifies, until the engine stops. And when the engine stops, when plate tectonics ceases, Earth will become like Mars, geologically dead, a single static crust. No more mountain building, no more earthquakes, no more volcanism, no more supercontinent cycle. And without the cycle, without the breakup assembly rhythm, evolution will slow, stagnate. Life will persist, but it will stop innovating. Stop diversifying. The planet will become static, boring, dead in all but the technical sense. But that's billions of years away. For now, the engine runs. The plates move. The continents drift. The cycle continues. And we are passengers, witnesses, products of the breakup phase, living in the calm, enjoying the dispersed continents, the moderate climate, the high biodiversity, the ecological abundance. But the convergence has begun. Africa is closing the Mediterranean. Australia is approaching Asia. The Atlantic will reverse. And in 250 million years, the continents will collide. Pangaea Ultima will form. The extinction will come. And life will do what it always does. Retreat, survive, wait. And when the breakup comes, life will explode. Again. The dance continues, inexorably, unstoppably, and Earth doesn't care who gets stepped on. There's a map that geologists use, a simple map. It shows plate boundaries, divergent boundaries where plates move apart, convergent boundaries where plates collide, transform boundaries where plates slide past each other. And on this map, you can see the future written in the present. Every convergent boundary is a future collision. Every subduction zone is a continent or island arc being consumed. Every mountain range is a supercontinent under construction. Look at the Mediterranean. The boundary between the African plate and the Eurasian plate is marked by a line of subduction zones, collision zones, and transform faults. That line is moving, shifting northward. The Mediterranean Sea, 600 kilometers wide at its widest point, is shrinking. In 50 million years, it will be half that width. In 100 million years, it will be gone. And Africa and Europe will be one. Look at the gap between Australia and Southeast Asia. The Banda Sea, the Timor Sea, the Arafura Sea, ocean basins separating Australia from the Sunda Shelf. That gap is closing, 7 centimeters per year. In 50 million years, the gap will be half its current width. In 70 million years, collision. Mountains will rise in New Guinea, Indonesia, Northern Australia, and the continents will merge. Look at the Atlantic, currently widening. But the oceanic crust near the margins is old, cold, dense. The North American margin, the South American margin, the African margin, all have old, dense crust offshore. And old, dense crust wants to sink. It's only a matter of time before a subduction zone initiates. Models suggest the most likely location is along the eastern margin of the Americas, the Atlantic subduction zone. Once it forms, the Atlantic will begin to close. The Americas will reverse direction, and convergence with Afro-Eurasia begins. This is not speculation. This is extrapolation, taking current velocities, current trajectories, and projecting them forward. The details are uncertain. The exact timing of subduction initiation is unpredictable. The exact configuration of Pangaea Ultima depends on which subduction zones dominate. But the general pattern is clear. Convergence, collision, supercontinent. And once the supercontinent forms, the clock starts ticking on the next extinction. But let's pause, because there's a question that needs asking. Why does Earth do this? Why does the planet assemble and shatter supercontinents repeatedly? What drives the cycle? The answer is heat. Earth's interior is hot, 4,000 degrees Celsius at the inner core boundary, 3,000 degrees in the outer core, 1,500 degrees in the upper mantle. That heat comes from 2 sources. Primordial heat, left over from Earth's formation 4.6 billion years ago, when countless impacts converted kinetic energy into thermal energy. And radiogenic heat, produced by the decay of radioactive isotopes. Uranium-238, Thorium-232, Potassium-40. These isotopes decay slowly, releasing energy, keeping the interior hot. And heat wants to escape. Thermodynamics. Heat flows from hot to cold. Earth's interior is hot. Space is cold. So heat flows outward, from the core to the mantle, from the mantle to the crust, from the crust to the atmosphere, and ultimately into space as infrared radiation. But the mantle is solid. Mostly, it's rock, silicate minerals. And solid rock doesn't conduct heat efficiently. So instead of conducting, the mantle convects. Hot rock rises, cool rock sinks. Slowly, a few centimeters per year. But over millions of years, that convection transports enormous amounts of heat. And convection in the mantle drives plate tectonics. Rising mantle material reaches the base of the crust, spreads laterally, cools, and sinks back down. The spreading creates divergent boundaries, mid-ocean ridges, where new crust forms. The sinking creates convergent boundaries, subduction zones, where old crust is consumed. The lateral flow moves the plates, continents drift, oceans open and close, supercontinents assemble and break apart. But here's the key insight. Mantle convection is not uniform. It's not a simple symmetric pattern. It's chaotic, turbulent, driven by temperature differences, composition differences, phase transitions in minerals. and it organizes itself into large-scale patterns. Convection cells, plumes, downwellings. One particularly important pattern is the superplume, a massive upwelling of hot mantle material, thousands of kilometers across, rising from the core mantle boundary all the way to the base of the crust. Superplumes are rare. Only a few exist at any given time. But when they do, they have profound effects on the surface. A superplume rising beneath a continent heats the crust from below. The crust expands, thins, cracks. Rift valleys form. Volcanoes erupt. Flood basalts pour out. Millions of cubic kilometers of lava. The continent splits. Fragments drift apart, and a new ocean basin forms. This is how supercontinents break apart. A superplume rises beneath the supercontinent. The interior, already hot and dry, becomes volcanically active. Rifting begins. The supercontinent fragments, and the pieces disperse. But why do superplumes form beneath supercontinents? The answer is thermal insulation. A supercontinent, by concentrating all the continental crust in one area, acts as a blanket, an insulator. Continental crust is less dense than oceanic crust. It doesn't conduct heat as well, and when it's concentrated over a large area, it traps heat in the mantle below. Imagine a pot of water on a stove. If you cover the pot with a lid, the water heats up faster. The lid traps heat. A supercontinent does the same thing. It sits on top of the mantle, trapping heat, and the mantle beneath the supercontinent gets hotter. Hotter mantle is less dense. Less dense mantle rises, and a superplume forms. The superplume rises, hits the base of the supercontinent, heats it, weakens it, cracks it, and the supercontinent breaks apart. The insulation is removed. Heat escapes. The mantle cools. Convection reorganizes. And the fragments of the supercontinent drift. But they don't drift randomly. They drift in patterns controlled by mantle convection. And mantle convection, driven by heat flow, tends to organize continents into clusters. Fragments drift apart, but they also drift toward downwellings, cold, sinking mantle, subduction zones, trenches, and eventually the fragments converge again, collide, assemble into a new supercontinent. The cycle is self-perpetuating. Supercontinent assembly concentrates heat. Heat buildup creates a superplume. Superplume breaks the supercontinent. Fragments disperse. Mantle cools. Convection reorganizes. Fragments converge. Supercontinent reassembles. And the cycle repeats. This is why Earth assembles and shatters supercontinents. It's a thermal cycle, driven by heat flow, mediated by plate tectonics, inevitable as long as the interior remains hot. And the cycle has a time scale, roughly 600 million years. Assembly takes 100 to 200 million years. Tenure, the period when the supercontinent is stable, lasts 200 to 300 million years. Breakup takes 100 to 200 million years. Dispersal, the period when continents are scattered, lasts 100 to 200 million years. Total, 400 to 800 million years. Average, 600 million years. This is called the Wilson cycle, named after Canadian geologist John Tuzo Wilson, who first recognized the pattern in the 1960s. Open ocean basin, Atlantic type, close ocean basin, collision, mountain building, supercontinent, rift, open new ocean basin. Repeat. Earth has completed at least 5 Wilson cycles, possibly 6. Year, Kenoland, Columbia, Rodinia, Gondwana, Pangaea. And now, the dispersed phase leading to Pangaea Ultima. Each cycle lasting roughly 600 million years, meaning Earth's history 4.6 billion years, contains about 7 cycles. Maybe 8 if we count the poorly documented early ones. And each cycle has shaped life. Assembly creates extinction pressure. Breakup creates evolutionary opportunity. The cycle is a metronome, keeping time, pacing evolution, forcing adaptation, pruning the tree of life, enabling diversification. Without the Wilson cycle, Earth's biosphere would be different. Less dynamic, more stable, possibly more sterile. The cycle, as brutal as it is, drives innovation, forces organisms to adapt or die. And over billions of years, that pressure has created the incredible diversity we see today. But here's the uncomfortable truth. The cycle doesn't care about us, doesn't care about humanity, doesn't care about civilization, doesn't care about intelligence or consciousness or culture. The cycle operates on geological timescales, millions of years, tens of millions, hundreds of millions. Human lifetimes are irrelevant. Human history, 10,000 years of civilization, is a rounding error. Homo sapiens, 300,000 years old, is a blip. The continents are moving toward Pangaea Ultima. The collision is scheduled. The extinction is coming. And there's nothing we can do to stop it. We can't halt plate tectonics, can't prevent continents from converging, can't avoid the climate catastrophe that supercontinent assembly brings. All we can do is what every other lineage has done: adapt, migrate, survive, or go extinct. But unlike every other lineage, we have one advantage: foresight. We can see the future, model it, predict it, understand it. We know Pangaea Ultima is coming. We know what it will do. We know the timeline. 250 million years. That's a long time. Longer than the entire history of mammals. Longer than the reign of the dinosaurs. Long enough for evolution to work. Long enough for our lineage to change beyond recognition. If Homo sapiens as a species survives for another 250 million years, we won't be Homo sapiens anymore. We'll have evolved, speciated, become something else, or many things. Our descendants might be adapted to the heat of Pangaea Ultima's coasts, might have metabolisms that tolerate 70-degree temperatures, might be small to reduce surface area and minimize heat gain, might be nocturnal to avoid the worst of the day's heat, or they might have left Earth entirely, spread to other planets, Mars, Europa, Titan, exoplanets around other stars. If we solve interstellar travel, if we build generation ships or develop suspended animation or extend lifespans indefinitely, we could colonize the galaxy. Make the supercontinent cycle irrelevant. Let Earth do what it wants. We'll be elsewhere. Or we might not survive. Might go extinct long before Pangaea Ultima forms. Climate change, nuclear war, asteroid impact, pandemic, artificial intelligence, ecological collapse. Any of these could end us within the next few centuries. And if we go extinct, the planet continues. Life continues. The Wilson cycle continues. Other lineages adapt, radiate, evolve. And in 250 million years, whatever dominates Earth's ecosystems will face the same challenges we would have faced. The cycle is indifferent. It doesn't favor intelligence, doesn't reward foresight. It operates on heat flow and convection and plate motion. And life, all life, is just along for the ride. But let's bring it back to the present, to the here and now. Because while Pangaea Ultima is 250 million years away, the lessons of the supercontinent cycle are relevant today. We live in the dispersed phase, the safest time, the most hospitable climate, the highest biodiversity, the greatest ecological opportunity, and we're squandering it, driving species extinct, destabilizing climate, degrading ecosystems. We're creating a self-inflicted extinction event during the one phase of the Wilson cycle when extinction pressure is naturally low. This is not inevitable. This is choice. Climate change is a choice. Habitat destruction is a choice. Overexploitation is a choice. We have the knowledge, the technology, the resources to live sustainably, to preserve biodiversity, to stabilize climate. We choose not to, and that choice has consequences. The supercontinent cycle will eventually drive another mass extinction. Pangaea ultima will kill 60 to 80% of species. But that's 250 million years away. What we're doing now, driving extinction rates 1,000 times above background, is happening in decades. We're compressing millions of years of natural extinction into a geological instant. And we're doing it during the phase when life should be thriving. The irony is brutal. We live in the best possible time. Dispersed continents, moderate climate, high productivity, the interglacial window between ice ages, the Holocene. The most stable climate Earth has experienced in millions of years. And we're destabilizing it, heating the planet, acidifying the oceans, clearing forests, overfishing, polluting. We are creating an extinction event during a time when the planet's natural cycles are giving life every advantage. And future geologists, if they exist, will see this in the rock record. A sudden spike in extinction rates during the late dispersal phase of the Pangaea ultima Wilson cycle, caused not by supercontinent assembly, not by volcanism, not by asteroid impact, caused by one species, Homo sapiens. That's our legacy. If we continue on the current trajectory, a thin layer in the rock record marking the Anthropocene, the age of humans, defined not by our achievements, but by the extinctions we caused. But it doesn't have to be that way. We can change course, stabilize climate, protect ecosystems, preserve biodiversity. We have the dispersed phase working in our favor. Moderate climate, high productivity, ecological resilience. If we act now, we can avoid the self-inflicted extinction and allow life to continue thriving until the next natural cycle kicks in. 250 million years from now, when Pangaea ultima assembles. And that extinction, at least, will be unavoidable, natural, part of the cycle. But the extinction we're causing now is not natural. It's preventable. And whether we prevent it or not is a choice we're making right now, in this moment. In this brief window of geological stability, the continents are moving. Africa is closing the Mediterranean. Australia is approaching Asia. The Atlantic will reverse. And in 250 million years, the continents will collide. Pangaea ultima will form. The climate will become extreme. The interior will become uninhabitable. Life will retreat to the coasts. 60 to 80% of species will go extinct. But that's the future. Distant, inevitable, beyond our control. The present is different. The present is ours. We live in the dispersed phase, the calm between catastrophes, the golden age of biodiversity. And what we do with that opportunity will define us, not as a species that lasted 300,000 years, but as a species that either learned to live within planetary boundaries or didn't. The supercontinent cycle doesn't care. Earth doesn't care. The plates will keep moving. The continents will keep drifting. The cycle will continue, with us or without us. But we care, or we should. Because we're the first species in 4 billion years to understand the cycle, to see it operating, to predict the future, to recognize the pattern. And that understanding comes with responsibility, not to stop the cycle. We can't. But to navigate it wisely, to preserve life during the phases when preservation is possible, to recognize that the dispersed phase is a gift, a window, a brief moment of planetary hospitality, and to use that moment not to destroy but to protect, not to exploit but to sustain, because the cycle will continue. Assembly, breakup, dispersal, repeat, for billions of years, until the planet's interior cools, until plate tectonics stops, until the engine dies. And when that day comes, when Earth becomes geologically dead like Mars, the supercontinent cycle will end. And so will the driver of biological innovation. The pruning, the radiation, the forced adaptation. Earth will become static, and life, if it still exists, will stop evolving, stop diversifying, persist, but not progress. But that's billions of years away. For now, the engine runs, the cycle continues, and we're here, witnesses, participants, products of the breakup phase, living in the calm. The convergence has begun. The next supercontinent is under construction. The future is already written in the motion of the plates, but the present is still ours. And how we use it, how we navigate the calm, how we treat the planet during this brief window of hospitality will determine what legacy we leave. In the rocks, in the fossils, in the thin layer that marks our time, will we be remembered as the species that understood the cycle and acted wisely, or the species that understood the cycle and destroyed anyway? The continents don't care, but we do. And that has to be enough. The dance continues. The plates move, the supercontinents assemble and shatter, and life, tenacious and adaptable, endures. Through assembly, through extinction, through breakup, through radiation, over and over, for billions of years. This is Earth's rhythm. This is the supercontinent cycle, and we are part of it, whether we like it or not, whether we survive it or not. The future is collision. The future is Pangea Ultima. The future is extinction and recovery and the cycle repeating. But the present is dispersal. The present is opportunity. The present is ours. Use it wisely, because the continents are already moving toward their next embrace. And when they collide, Earth won't ask permission, won't offer mercy, won't pause for reflection. The dance continues, inexorably, unstoppably, and Earth doesn't care who gets stepped on. Thank you for watching. If this exploration of deep time and planetary cycles has given you a new perspective on our moment in Earth's history, please consider subscribing and sharing this with others. We're all navigating this brief window of geological calm together. Understanding where we've been and where we're going might help us make better choices about what we do right now. Until next time, remember, the continents are moving, the cycle continues, and how we respond to that knowledge defines us.